Hello, students. Good evening. Welcome to Vedantu, Karnataka. This is Catherine, your physics master teacher. Quickly, can you let me know if I'm live? If I'm audible and visible? Mhm. Thank you, Sumit Kumar. Hi, Harshita. Hi, GM. Just check if I'm audible and visible. Hi, Dharmaraj. Welcome to the lesson. Okay, quickly, as usual, all of you send the link to all your friends, all your groups. Let them all join. Hello, Shivani. How are you? Hello, hello. It's a Saturday evening, and what are all your plans? Ma'am, read my comment. Don't ignore. I read your comment, dear. I'm not ignoring you. Okay, don't worry. Okay, so let's do part 2 of. Hmm, 1 second, students. There's a small. You're all able to hear me properly, right? Yes, I think I am able to hear me properly. Sumit Kumar, I will read. Ma'am, why don't you teach using digital board like how you taught before one day of SSLC exam? That is physics from there itself, I got. Okay, the thing is I teach from home, okay, and I don't have a board at home. That's why I'm not able to teach with a digital board. That day I went to the studio to teach. Okay. My God, Sumit Kumar, you've watched all my lessons. Okay, so let's start today. So last class, what all did we discuss? We discussed all of Newton's laws. We discussed Newton's first law, second law, third law, all laws we discussed. Today, we're going to discuss the concept of tension. Okay? Not the tension that you have before your exam, but this is tension in physics. Yes? Any idea on what is tension? Tension is basically, sorry, the force that is applied on strings. Okay, so I'm sure all of you have done the simple pendulum experiment in your first PU. Yes, you might have done that in lab, right? So what you have a holder. From there, you suspend a string to which a simple pendulum is attached, and you count the oscillations. So the force experienced by this string is called tension. Okay, so tension is basically the force experienced by strings or objects like that. So let me draw a picture for that. Now if you have some support, okay, and you have a string, you attach a mass to it. Okay, so this mass has a weight. Yes, so it has a force that it experiences downwards, and this force is because of two things. The main thing is gravity. Yes, there is gravity acting downwards, and the weight of the object is also acting downwards. Is my face cut off into. Okay. The weight of the object, which is mass. Not weight is not mass, but the mass of the object is also acting downwards. Okay. So the two forces, these two together acts downward, and this is called mass. Okay. Sorry. Wait. Wait. This is called weight. Yes? Very good, Shivani. Very good. Okay? So weight is experienced downwards. Now my question to all of you smart little ones out there is, if weight is experienced downwards and weight is pulling this block downwards, why is this block not falling down? Why is the string not breaking and why is the block not falling down? That is my question. Any answers? Do you understand? So this is the roof. From here, there's a string and there's a mass attached. Okay, so this experiences a force downwards because of its weight. But the string is not breaking. This is not falling down. Why? Why? The main reason is because there is an upward force in the opposite direction. Very good, Sumit Kumar. And that upward force is called tension. Yes. So this upward force balances the downward force and the block stays where it is. Now, if tension was not there, the downward force is more, the block would fall down. But because there is an upward force which is equal and opposite. Last class we learned balanced forces and unbalanced force. So here tension and weight both are balanced forces. They're equal and opposite in direction. So the total force acting on the block is 0. So the block just stays where it is. Yes? Very good, Sumit Kumar. Yeah? Okay? So this is tension. Tension is the upward force experienced by a string. Now, not just a string, for your fan. Okay? So at home, you all have your fan. Okay? I'm very bad at drawing. So let's imagine this is your fan. Yeah? This fan also has its weight, which is mg acting downwards. But the fan does not fall on your head. And sometimes it does, but that is because of, problems in the fixing and all that. Technical issues. But generally a fan does not fall down because it has an upward force and tension which acts upward. So tension and weight are balanced, so the fan stays where it is. Is this fine? Yes, is it clear? Okay? Shall we move on? Okay. Next, let's look at the concept of apparent weight. Are you all with me? Or it's a Saturday and you're all busy at home watching TV and all that? No, ma'am? Not clear? Does no, ma'am mean not clear? Tension is not clear. What is your doubt in tension? It is just an upward force, dear. It is just an upward force experienced by strings or, anything that is opposite to the downward weight. Can you tell me what is not clear there, Sumit Kumar? Okay. So tension is basically it is the force that is transmitted through a string, a rope, a chain, anything like that. Okay. It's always in the opposite direction. So if there's a force downwards, tension will be in the opposite direction. Yes. See, when I don't know, in wells and all, you put buckets to, take water. Nowadays, very rarely people do that. But then earlier, people used to draw water from wells using rope. So what do? They put the bucket at the end of the rope, they put it into the well and then they pull it. Yes. So the rope is what pulls the bucket up. And then the force by which it comes up is called tension. Okay. So tension is a force that's like a force on a string or a rope that just pulls it up. Tension always pulls. Is this clear? I don't see anything in the chat. Okay. So I can write that point also here. Tension always pulls. It does not push down. Whatever force is pushing down, tension always pulls in the opposite direction. Uh, yeah, you can use. Okay, Sumit Kumar says his physics teacher gave an example of door for tension. See, you can use that example also. So imagine you tie a rope to a door. Okay, you have a door and you tie a rope to it. You tie a rope to the door handle and you pull the rope to open the door. What happens? The rope becomes tight. So you are able to pull the rope because of tension. Yes, that is also an example of tension. I don't know if that is the example your teacher gave. Anyways, yeah, you've understood the concept, right? That's all that matters. Okay, next is the concept of normal reaction. Sometimes this is also called as, I'm really sorry. Sometimes this is also called as apparent weight. Have you heard of the term apparent weight? Concept of normal reaction or the concept of apparent weight. Apparent weight. Okay. So, have you ever thought about this? You're walking on the ground, okay? You're walking on the ground. There is obviously gravity pulling you down. Your weight also acts downwards. So, there is definitely weight, which is mass times gravity, acting in the downward direction. But simply when you're walking on the ground, you are not pulled into the ground. See, when you're walking at home, you don't break the floor and go inside. Even though weight is pulling you down, you don't go down. You're balanced on the ground. See, right now, if you're sitting or you're standing, you are standing on the ground. You're balanced, but there is weight pulling you down. But why don't you sink into the floor? Why don't you like all these superheroes? Why don't you break the floor and go inside? What happens? What is that one force that makes you stay on the ground? Have you ever given that a thought? Anybody? Yes. Anybody? Anybody have thought about that? So the main reason for that is there is some upward force balancing it. Okay? The main reason that you don't sink into the ground is because there is an upward force balancing it. Yeah? And that upward force is not tension here because you are not made out of any string or rope. In this case, that upward force is called R, which is called normal reaction force. Okay? So, normal reaction force is the upward force that cancels out your weight. Okay? Now, let's take an example of a car. Okay? So, there's a car. This car also has weight, which is mg acting downwards. Yes. But this car also does not sink into the ground because it has normal reaction force or normal force acting in the upward direction. Now, this need not always be, in the same opposite direction. There are examples where you have a road like this, a road that is at an angle, okay? And this Yes, it acts perpendicular to the object. Very good, Shivani. I'm coming to that. So normal reaction force. Okay, imagine this is a slanted object. I mean slanted road, and there's a object here. Okay, so this object will also have its weight acting downwards, which is mg. But normal reaction will not be acting upwards. Normal reaction will always be acting perpendicular to the object. So it will be in this direction. Okay? Do you understand that? So whenever there is an object, it always has its weight acting downwards. Not perpendicular, it's always downwards. But normal reaction is an opposite force, but it always acts perpendicular to the object. Okay? So if the object is straight, normal reaction is up. The object is slanting, normal reaction is perpendicular to that. Now if there's an object like this, normal reaction is like this. Okay? Normal reaction is always perpendicular to the object. Is that clear to you? Now here some of you might ask me, how will you find the total effective force? For that you need to resolve this into horizontal component, vertical component, take sine theta, cos theta and all that. That also we will learn in this chapter itself. Okay, so that is very important for your KCET. So right now I want you to understand that if you have an object and it has its weight acting downwards, if it's not attached to a string or a rope or anything like that, it always has a normal reaction force acting perpendicular in the opposite direction. Okay? Okay? Is that clear to all of you? Yes? Yes? No? Can I have some thumbs up? Okay? Now what we'll discuss is, we will discuss some cases where, some cases regarding the lift. So those are very important things in this chapter. So we will look at the lift. Okay? So now we know this weight acting downwards, normal reaction acting upwards. Now we'll see how this can be used in a lift. Okay? So we will look at different cases. For a lift, we will look at different cases. Now let's look at the first case. First case is lift is at rest. Okay? So imagine this is a lift. Okay? And you are standing inside the lift. So this lift is at rest. Okay? So the lift is not moving. You are standing inside the lift. Very simple case. Did you all understand the case? Okay, there's a lift. The lift is not moving. There's no current. Imagine there's no current. The lift is not moving. You are inside the lift. Now let's resolve the forces that are acting on the lift. So obviously one main force is your weight, which is acting downwards. And if your weight is acting downwards, then there is normal reaction R acting upwards. So this much is there on the lift. Yes. So the total force, okay, the total force experienced will be the difference between the upward force minus the downward force. Yes. So the lift is at rest, right? So any force that you experience will be the difference between the upward force and the downward force, because those are the only two forces acting on your body. The difference in force, I will just write it as Fm. Okay? It is basically R minus mg. Now, from Newton's second law, what is force? Force is equal to mass into acceleration. So, instead of force, can I write it as mass into acceleration? Yes. Mass into acceleration is equal to R minus mg. Okay? Now, this is a lift that is at rest. This lift is not moving. So, what is the value of acceleration of this lift? Tell me, if a lift is not moving, how much will it accelerate? What is acceleration? Increase in speed with respect to time, or increase in velocity with respect to time. Yeah, let's put velocity. Increase in velocity with respect to time. Increase or decrease. Change in velocity with respect to time. But here this lift is not moving. So obviously, isn't the acceleration going to be equal to 0? Yes, acceleration will be 0. So now m into 0 will be R minus mg. M into 0 is 0. So R is equal to mg. So when I started this problem itself, you might have thought, ma'am, if a lift is at rest and a person is not moving, how will the upward and downward force be different? It should be the same because there is no movement. Yes, we have just proved that. Okay? So when a lift is not moving and there's a person standing inside the lift, his upward force and downward force are going to be the same. There is no movement. Okay? So R upwards and mg downwards are balanced. So he has a balanced force. Okay, let's look at the questions. Weight increases in lift as the lift goes up and weight decreases as it goes down, and weight would remain constant when the lift is at rest. Ma'am, is it correct? Please say ma'am. Okay, all of these cases we will discuss now. Okay, and after I discuss all this, Sumit Kumar, you tell me if this is correct. Okay, let's see if you listen to the class. Alright. All these cases we are going to discuss now. So the first case that we discussed is a lift at rest. Any doubts here when the lift is at rest? Okay. Next case. Sorry. The next case is you have a lift. Okay. There is a lift. You are standing inside the lift. Okay. And the lift is moving down. Alright. Yes. Okay. So here lift is, okay, let's take a general case. Lift is moving. It can move up or down with uniform velocity. Okay. So that's the lift. Okay. And on the lift, you can move up or down, but the speed, velocity is not increasing. Let's say the velocity is 20. It's going up with 20, coming down with 20. It does not become 30, 40, 50, or it does not become 10, 5, 0. It is not increasing or decreasing. Same velocity you're going up, same velocity you're coming down. Okay? Is the case clear? I think I should put it here. Yeah. Is the case clear? There's a lift. It's moving up or down with the same uniform velocity, means same value of velocity. For example, if the velocity is 30, it's always going to be 30. So obviously it has two forces. Weight equals mg acting downwards, R acting upwards. Those are the two forces acting on the body. Yes. Now, here, what is the value of acceleration? In the previous case, the body was at rest, so obviously acceleration is 0. Here, he has same velocity. So what is acceleration? Yes, it is 0. Why is it 0? Because acceleration is what? Change in velocity by time. Here is velocity changing? No. So the change in velocity is 0. The velocity is the same. So there is no change in velocity. So acceleration is 0. So now let's do the derivation. So first thing, as always, the net force. The net force is basically difference between upward force and downward force. So mg minus r. So mg is equal, F is equal to ma. So instead of F, I can write it as ma, Newton's second law, is equal to mg minus r. If acceleration is 0, this will be 0. So 0 is equal to mg minus r, and then mg is equal to r. Okay. So students, in these cases, you don't have to bother on if you're writing it as mg minus r or r minus mg. Because anyways, you're going to equate it. It's going to be equal. Okay. So when that matters, I'll tell you. Okay. So in some cases, you need to put mg first. Some cases, you need to put r first. We will come to those cases. But here, this is clear. So these are the two cases where r is equal to mg. Okay. What are the two cases? Where r is equal to mg when a lift is at rest and when a lift is moving with uniform velocity. Basically, whenever acceleration is 0. Okay? Is this clear? I think now it's visible. I hope my face is not covering it. Yes. Any doubts here? So students, these are very important, okay? When it comes to KCET perspective and all that, it is very important. Okay? Okay. All right. Now let's move on to the next case. So this same thing applies when the lift is moving up or the lift is moving down. Mg equals r. So whenever acceleration is 0, mg is equal to r. Okay? Yes? Shall I move on to the next case? Okay. Next case. Next case is when you have a lift moving upwards. Lift is moving upward. Okay? With acceleration. Alright? So next case is the lift is moving upwards with an acceleration. So let's draw the lift. So this is the lift. Okay? This is the lift. This is that person. Yes. And he has his weight mg acting downwards. Normal reaction r acting upwards. Now he will have the lift is moving upwards. So acceleration will be upwards. Okay? So this is our case. Yes. Yeah, I have two students in my class, Shivani and Sumit Kumar. They keep motivating me like anything. Okay. Okay, so this is the case. We're going to solve this. Lift is moving up with an acceleration. Okay. Yes. So now in these cases, students, when you write down the net force, it's important on which force you write first. Okay. So net force or FM. Okay. Here, it's again the difference between the two forces, but you should take the force in whichever direction the lift is moving, that force you should take first. Okay. So for example, here, lift is moving up, acceleration is up. So which is the upward force? Normal reaction. So R you will take first. Okay. So keep that in mind. That's like a trick. Okay. That's a hint that you should be using. So whenever normal reaction and force they're not equal, you should take the force in which the direction in which the lift is moving, that force you should take first. So here lift is moving up with an upward acceleration. So the normal reaction R is what you should take first because R is the force in the direction of the acceleration. So obviously net force is what? R minus mg. Okay? R minus mg. Force again, Newton's second law, force is equal to ma. ma is equal to R minus mg. How will I find R? R will be ma plus mg. Yes, R is equal to ma plus mg. Now from this, what can I say about ma and mg? Can I say that R would always be greater than mg? Can I say that? How can I say that? I'll explain with an example. So let's say ma is equal to 2. Okay? And mg is also 2. What will R be? R will be 2 plus 2, which is 4. So in this case, can't I say R is greater than mg? Because 4 is greater than 2. Isn't it? Whatever numbers I put there, see, you have a number mg. To mg, you are adding another number. That together gives you R. So every time R will be bigger than mg. Because what is R? mg plus ma. ma also added together gives you R. So R will always be greater than mg. Yes. Now what does R greater than mg mean? That means the upward force is greater than the downward force. Which means that since there is a higher upward force, this means that the person will feel heavier. Will feel heavier. Okay. So this is the answer. So this example here, this mathematical part you don't want. I mean, you don't have to write. Let's put this thing here. Yeah. Okay. Person will feel heavier. Okay. Is this clear to you? Okay, okay. Yes, yes, yes. No, yes, no. Can I have some response? Is this clear to all of you? So whenever there's a lift that's accelerating upwards, yeah, it's accelerating upwards, you will have the person being heavier. Okay? Yes. Okay, little I got it. Only little. Why not full? From where didn't you get it? This you should get because the next case is just like this. This you should get it fully. Did you understand till here? Yes. Okay. See, when a lift is moving upwards with acceleration, R is equal to ma plus mg. So R is greater than mg. So why the person feels heavier? Is that what you haven't understood? Okay, I can give. I don't get any response in the chat. See, students. See, when you're in a bus, okay? Okay, now got it. Okay, anyways, I'll just see. When you're in a bus, okay? And then if the bus suddenly speeds up, if the bus suddenly moves fast, what happens? You will fall down. You'll go sit down. No. If you're standing simply on the bus, you'll fall down. That's because the the seat you'll basically if you're sitting also you'll basically go a little more down. Okay, next time you get on a bus, you try that. If the bus driver is going fast, you'll actually feel this movement. You'll feel a little more that you're being seated to the ground a little more, and that is mainly because the seat has to push you harder to accelerate you along with the bus. Okay, so here also what happens? See, weight, the sensation of weight, that comes from normal force. Okay, so normal force is the upward push that you have. So when the lift is going up, the floor must push you harder, not just to balance your weight, but also to balance the acceleration. Okay, so when you go up, this normal reaction has to increase because now it just does not have to balance weight, it also has to balance acceleration. Okay, that's why you feel heavier. So you feel a big push in the upward direction. Okay. Okay, I think let's move on to the next one. Next case. I'm really sorry for that, students. Next case will obviously be the opposite of this. Lift is moving downwards with an acceleration. Okay. So lift moving downward with an acceleration. Okay. Lift moving downward with an acceleration. So let's draw the lift. You are standing inside the lift. And here, again, there are two forces. Your weight is equal to mg acting downwards, normal reaction acting upwards. And then here, the acceleration of the lift is in the downward direction. Okay? Acceleration of the lift is in the downward direction. Now, here, the only difference that you do when you do the derivation is, when you're writing the net acceleration, which value you will subtract first? The value in the direction of acceleration. So, what is in the direction of acceleration? Acceleration is downwards, weight is also downwards. So, what you should do is, you should put mg first. mg minus r. In the previous derivation, what did you put first? You put normal reaction first. Understood? Why did you put normal reaction first? Because you are going up. So when you are going up, normal reaction is in the upward direction. Now you are coming down. Now when you are coming down, weight is in the downward direction. Okay? So here, force is basically mass into acceleration, which is mass into gravity minus normal reaction. Now, how will I find R? So, if I take R to the other side, it will be mg minus ma. Now, here you tell me, would R be greater than or less than mg? Will R be greater than mg or less than mg? It will be less than mg. Why? Think of put numbers and see. See, whatever value R has, it will always be mg minus some number of ma. Okay, so if mg is 10 and let's say ma is 5, R will be only 5. So 5 is obviously less than 10. You understand? R will always be mg minus something. So it will be less than mg. Okay? Now what does this mean? This means that the person will feel lighter. Okay? So the conclusion to this is person will feel lighter. Okay? Is that clear to you? So if a lift is moving downwards, then what happens? The acceleration is downwards. So you don't have to exert a lot of force because you are going along with the lift. So you will feel light. But when you're going up, your weight has to be balanced in the opposite direction. So you will feel heavy. So you can actually try this if you're living in apartments. Take a weighing machine, go stand on the lift. So initially when the lift is at rest, you stand on the weighing machine, you'll see a weight. Now you go up, you will see your weight is changing. When you go down also, you will see your weight is changing. Only if your lift is accelerating. If your lift is going with the same velocity, then you will find no change. Okay? Yes, no. What happened, Sumit Kumar? What happened to you? Is this clear, students? So when a lift is moving downwards with an acceleration, you will feel lighter. Now when you are moving up with an acceleration, you will feel heavier. Okay? Next case. So the only difference between this derivation and this derivation is what? The only difference is the term that you took first. Here the lift was going up. So the force along with the upward direction is R. Acceleration and R are in same direction. So you take R first. Here lift is going down. So acceleration and mg are in the same direction. So you take mg first. Okay? Yes? Alright. Next question. Next question. Next case. So the next case is the free fall of the lift. Okay? Hey, what happened? Free fall of the lift. Okay. So for free fall of the lift, what happens? You have a lift. Okay. You are standing inside the lift. Like always, there is mg acting downwards. There is normal reaction acting upwards. Yeah. mg acting downwards, normal reaction acting upwards. What do you mean by free fall of a lift? Free fall of lift means, say I think you've seen that lift is held by very thick, strong ropes, and these ropes keep moving. That's how the lift goes up and down. Imagine the rope breaks. Okay, lift is up, rope breaks. What happens? The lift just freely falls down. Initially, it falls, it comes down with control because it is controlled by the rope. But if the rope is cut, it just comes and falls down. Isn't it? Yes? Yeah? So there's a lift and it's cut, it just freely falls down. Okay? Now, the net force. The net force will be, here the lift is freely falling down. Okay? So it's falling down. So which direction is it falling? Down. So which is the downward force? Mg or R? Mg. So Mg should come first. Mg minus R. Yes. Newton's second law. Ma is equal to Mg minus R. Now, one thing that you need to know here is the lift is freely falling down. So what is the value of acceleration of the lift? Acceleration of the lift. Acceleration of the lift is how much? If you know that, then this derivation is done. Very easy. How will you find that? See, if I have, what do I have? What do I have here? Something that's light. Okay, I have a wallet. Okay, so this wallet, it just freely falls down. What happens? It freely falls down. Okay, same thing. Imagine this is a lift, it's freely falling down. So what happens? With what value of acceleration is it falling down? Yes. Good, good, good. You are very smart. The acceleration value is equal to the value of gravity. Because I am not pushing it down, I am just leaving my hand, it falls down. So the moment it falls down, it is pulled down by gravity. See, just like the apple fell down on Newton's head, the apple freely fell down, and it fell down because of gravity. So, can't I say ma is equal to mg? M and m is the same. So, acceleration is equal to gravity. Then, ma is equal to mg. Can I say that? So, then in that case, here, ma and mg are the same, so won't they cancel out? So then normal reaction will be equal to 0. Okay, so depending on the normal reaction, you experience weight. If normal reaction is high, you experience a lot of weight. If normal reaction is less, you experience little weight. If normal reaction is 0, what do you experience? Yes, you experience weightlessness. Weightlessness. Okay? So when normal reaction is 0, you experience weightlessness. Very good. Very good, students. It's G 9.8 or 10. That is your acceleration. So here I don't put numbers because anyways I have to cancel it. So I can just write it as G. Okay? Yes. Sorry. Is this clear to all of you? Clear, clear, clear. Quickly, quickly, quickly. Let me know in the chat if this is clear to all of you. Come on, where's the Josh? My question itself has no Josh, no? Okay? Next, one last case. Okay, we're going to wind up lift with that one last case. What is that last case? Here, what's going to happen is, when the lift moves down, okay? So, lift moves lift moves downwards with acceleration greater than gravity. Okay? So lift is moving down with acceleration greater than gravity. So definitely it is not freely falling. So this is the lift. You are standing inside the lift. Okay? And then there's mg acting downwards. And then there is normal reaction acting upwards. But in this case, the lift is coming down with an acceleration, but the value of acceleration is greater than gravity. Okay, let's do the math. So what all will we do? First question, the net force. Okay, net force will be, in which direction is the lift moving, up or down? Up or down? Quickly. Down. So which force should come first? mg minus r. Newton's second law, F is equal to ma. ma is equal to mg minus r. So r is equal to mg minus ma. Okay. So since acceleration is greater than gravity, mg minus ma, should it be positive or negative? mg minus ma, will it be positive or negative? You tell me. Okay. mg minus ma. If acceleration is greater, obviously this is like 5 minus 10, isn't it? So this will be negative. mg minus ma, this will be negative. So r will be what? Negative. Okay. So if the lift is moving downwards, the resultant or normal reaction will be negative. Okay. I am appreciating both of you, Sumit Kumar. Both of you said 9.8, no? Yeah, I think both of you did. Okay. Is this clear to you? See, weightlessness, how, ma'am? See, weightlessness because, see, one thing you should know is you feel weight because of your normal reaction force. See, the downward force is always constant. If you're standing on the lift, lift is moving up, lift is moving. However you move, your downward force, mass and gravity it is always constant. But sometimes you feel heavy, sometimes you feel light. All that is because of how normal reaction changes. So you can see in the first case, when normal reaction was high, you felt heavier. When normal reaction was low, you feel light. If normal reaction is zero, you feel nothing. You feel weightlessness. Okay. So you feel your weight because of normal reaction force. So depending on how normal reaction force changes, it changes, how you feel. So why did you feel heavier in the first case? Because normal reaction was greater. You felt lighter because normal reaction was less. Now if normal reaction is zero, you will feel nothing. Okay. All right. Is that clear, Sumit Kumar? Yes, no? Can I have some response? Okay. All right. Okay. Okay. All right. Now, in the next case, what we're going to do is we are going to, write the formula for a system with two masses. Okay. I'm sorry. Really sorry. Really sorry. So, see, in these cases, it was you and the lift. Now, let's consider a pulley. Okay. A pulley is where you can, move a wire. You might have all. Hi, Varshita. Welcome to the lesson. Hey, Sumit Kumar, normal reaction is greater or lesser depending on, the acceleration and all that. That is what we derived here. Here, see, when the lift is moving downwards, mathematically we proved, no, that normal reaction will be less. So if normal reaction is less, you will feel light. Okay? Now in this case, we mathematically proved that normal reaction will be greater. Okay, so when normal reaction is greater, what happens? You will feel heavier. Now in this question, we proved that normal reaction is 0. So if normal reaction is 0, you will feel weightlessness. Okay? Yes. Okay, now let's look at a system with a pulley. Okay, this is a pulley. And on the pulley, I put a string. To the string, I'm going to attach two masses. Okay? So this is a pulley. Okay? Those who don't know what is pulley, quickly go Google what is pulley. If you see the image, you'll understand. It's like a ring where you can transfer the rope. In wells and all, you use pulley. Okay? So there are two masses that are acted on the pulley. Okay? Now the first mass, let's call it mass M1. The second mass, I'll call it mass M2. Alright? Now here, the force that's acting downwards will be M1 into gravity. Here, the force that's acting downwards will be M2 into gravity. Now, these are both held by string, isn't it? Both are held by string. So, string has what force? It does not have normal reaction force, but it has tension. And tension is always perpendicular to the body in the opposite direction. So, here tension will be like this. Okay? Tension is in the upward direction. Is this figure clear? So there is a pulley, there are two masses. M1 is heavier, that's why it's down. So it will move like this. Okay? Tension is in the opposite direction. So from this clearly I can say M1 is greater than M2 because M1 is coming down. Okay? Okay. Now let's write down the forces acting here. Very good, Shivani. Very good, Sumit Kumar. Tension. Yes, that's the force acting on the string. So, first thing, we will do it for mass M1. Okay. So, for mass M1, what are the net force? Okay. Fm. The Fm can be written as anything. You can write it as Fn, Fnet. You can just put it as F. Okay. You can put it as Fn. You can put it as F. Anything is fine. Okay. I'm just putting it as a random alphabet. Okay, so the net force is how much? For mass M1, in which direction is it going? Downward. So it will be, which is the force acting downwards? M1G minus T. Okay, Newton's second law, F is equal to MA. So M1A is equal to M1G minus T. Okay. Is it clear? Yes, yes. Okay. Hello, freestyle. Toxic, why are you not attending my classes from the beginning? This is first for you class. You should be here, no? Okay. So M1A is equal to M1G minus T. Is this much clear? Now we'll do the same thing for mass M2. Okay. So for mass M2, what will we do? Again, let's say the net force. Here, the net force will be how much? M2 is going up or down, you tell me. Yes, M1 is going down, M2 is going up. So which is the force in the upward direction? Tension. So tension should come first. T minus M2G. Now again Newton's second law, M2A is equal to T minus M2G. So these are the two main equations, initial equations. Okay. M1A is equal to M1G minus T. M2A is equal to T minus M2G. Okay. T is tension, dear. Tension, tension. T is the upward force on the string, which is tension. See, on mass M1, what are the forces acting? M1G downwards and tension upwards. Okay. Since M1G is acting downwards and tension is acting upwards, and the mass is coming downwards, you take m1g first. Alright? Alright. So these are the two main equations. Any doubts? Okay, let's move on. We're spending too much time here. Let's move on. Now what I'm going to do is I'm going to add 1 and 2. Okay? Which color should I add it with? I'll take red. Okay? So adding 1 and 2, what will we get? Both are F net, no? So I can just ignore it. I can add 1 and 2. So m1g minus t is equal to, no. No, this m1a and m2a, right? So on the left hand side, it's m1a plus m2a is equal to m1g minus t plus m2g, no, t minus m2g plus t minus m2g. Okay? m1g minus t. Now this minus t and plus t will cancel. Okay? So what happens? This is m1a plus m2a is equal to m1g minus m2g. Alright? So students, this is a derivation where I'm going to find out tension of, a two-body system. Okay? Tension and acceleration of a two-body system or a system with two masses. I'm going to find tension and acceleration. Alright? Now, from this equation, I am going to find acceleration. How will I do that? So what I'm going to do? I'm going to find acceleration. So acceleration is common, so I will take that outside. So what remains? m1 plus m2 is equal to m1 minus m2. G is also common. So now from this, can't I clearly write acceleration is equal to m1 minus m2 into g, the whole divided by m1 plus m2. Can I write that? Yes. So this, I'm sorry. This is the formula for acceleration of a body or a system with two pulleys. Yes, this is important. Okay. It's easy, no? If you understand the concept, it's very easy. Isn't it? Okay. Yes. Okay. Now what I'm going to do is I'm going to also derive tension from this. Okay. So let's derive tension from this. So to derive tension, what I'm going to do is I am going to divide equation 1 and equation 2. Okay, I will divide equation 1 and equation 2. So what all will I get? m1a is equal to m1g minus t divided by m2a is equal to m2g minus t. Okay, so a and a I can cancel. A and a I cancel. So what remains? m1 by m2 is equal to, this is equal to there. Okay. Yeah. m1 by m2 is equal to m1g minus t divided by m2g minus t. Okay. Now what I'm going to do is I am going to cross. cross multiply. Okay. So I will cross multiply. So what will I get? I will get m1 into m2. See, that is, in order to get tension, you have to divide. You'll understand after I finish it. So to get acceleration, you have to add. To get tension, you have to divide. Okay. Because I should get an equation in terms of t. That is why I am dividing. Okay, Sumit Kumar. Okay. So m1 into, hey, 1 second. Nobody pointed this out. This equation is opposite. No. What is the equation? It is t minus m2g. Why didn't you point this out? T minus m2g. Yeah. Okay. So those who are watching it recorded, if you have pointed it out, very good. So m1 is equal to, m1 into, here this will become T minus m2g. T minus m2g, and this will be equal to m2 into m1g minus t. So let's open the brackets. So this will become m1 into t minus m2g into t is equal to m2 m1 into g minus m2 into t. Okay. Now what is the next step that we do? We can take m1 and m2 to one side. So m1t plus m2t is equal to m1 m2g plus m2g2. Yes, m1 m2g plus, one more mistake. Here this is not t, this is m1. Okay. Yes. Ma'am, how to talk with you, ma'am, about some motivation related doubts. Okay. So m1t plus m2t is equal to m1 m2g plus m1 m2g is what? 2 m1 m2g. Okay. So nothing else but 2 m1 m2 into g. Okay. So from this you can easily find out t. Quickly do it. How will you get t? T taken outside, m1 plus m2 is equal to 2 m1 m2g. Okay. Now what is t? T will be equal to 2 m1 m2g, the whole divided by m1 plus m2. Hey, what happened? Two m1 m2g divided by m1 plus m2. Very easy. Not easy, I agree. It's not easy. It's a little long, but if you understand, it's going to be easy. Okay? So how will you learn these derivations, students? What you should do is, once you do it along with me, yeah, and then once you try to do it by yourself, you will definitely get stuck somewhere. So go refer, correct it, do it again, write it, do it again. You might get stuck again, go refer, correct it, do it once again. Okay? You write and do it unless and until you are able to do it once without looking anywhere and not getting stuck. Only then you've learned it. Okay? So for KCET, you don't have to do all this, but for your PUC and CBSE or ICSE, whatever, physics derivations are always things that you forget. So writing and learning is the only thing that works. If you're by hearting, you might get confused. So understand what you're doing and write and study. Sometimes 4 or 5 times you have to write a derivation. It depends on each person's skill. Not skill actually, each person's learning ability. Okay, that keeps varying from people to people. So make sure you write it. See, sometimes when I was a student, not some derivations I write it once, I learn it. But some derivations, even if I write 7 times, I might not learn. I might be the 9th time I learn it. That's how you learn physics. Okay, so that is why all of you, I've seen lots of students tell me, Mom, I go to the exam hall, I forget. It's because you haven't written and practiced. Alright? Okay? Alright? Sumit Kumar, face to face we can meet. We have these Vedantu events, okay, where you students get chances to meet teachers. So all of us teachers will be there and you can also come, okay. So when those events happen, I will let you know in my classes. I will share that, okay. So at that time you can come, we can all meet. Okay? Okay, Sumit Kumar? Happy? Yes. So today we discussed derivations for lift cases. We looked at the concept of normal reaction. We also looked at the concept of tension. Okay. So in the next class, we will look at impulse, banking of roads and all that. We'll look at questions based on that. Okay. So today I'm not discussing questions because you need to know a little more of concept to do the questions. So those questions we will discuss in the next class. Is that clear to all of you? Yes. Are we good to go? Okay. Any doubts in today's class? If there's no doubts, I'll see you all tomorrow. So tomorrow the class will be a little early. It will be usually at 12 o'clock. Mainly at 12 o'clock. Not mainly, most probably at 12 o'clock. Okay? So please inform all your students. All your friends. Not for you, it's not students, no? All your friends to join me at 12 o'clock. Okay? Okay, so I'll see you all with another fantastic class in the next class. So until then, bye bye. See you. Take care of your health. Take care. Study well. And let's talk in life.